Well, here we are in the lab again. Welcome to episode 24 of the I/O board. I submitted the Gerbers, the latest revision, to PCB Way, and I got some new PCBs. I had to pay 30% tariff on these guys, which was kind of rough, but we got them. And right after I ordered the parts for this board, or when I was ordering the parts for the board, the flash chip package, not the chip itself, but the package that it comes in, the shape, form factor, is discontinued. So that means this main brain uses this flash chip and the I/O board uses this flash chip. So both have to get revisioned and changed for, it's the same style package, it's just a little bit bigger. And so we will have to change that. And also I messed up, and once again, and I don't know how I did it. And this is a good example of how the documentation can make you or break you, because if you document everything properly, you won't make mistakes as much. But I let my documentation kind of slide, and somehow the buffer chip for the data buffer between the SRAM and the microcontroller, the direction is backwards. So when the microcontroller tells it to write to the SRAM, it's reading from SRAM, which causes a bus conflict, and it just doesn't work. So that causes a jumper, a wire that we have to add to the board, and a little software fix, just like before on the prototype board. But since we have to do a revision on the package change of the flash, it'll get cleaned up on that. So the next revision will be the last revision, and then we'll be done with this project. So now we get to test the new design and play around with what it can do and do some tests and stuff like that. So let's waste no time and get to it. Okay, so like before, we have to take this connector here that goes on to the board on the end for the ribbon cable. This, since it has pins in the back behind there the soldering iron can't get to, we have to solder this in the oven. So before we had a little bit of trouble because my solder paste is kind of old. So it didn't flow as well as it should have. And solder paste is a pain in the butt when you don't have a screen for it. So if you're in production, you're going to have a screen, and you just screen that across there, put the parts on, boom, and it flows in nice. But we don't have that because it's a prototype, and we're not doing production. So what I found out on this one, this is the best way so far that I found. It works really good. So you take and you put a little dab of solder on each pad with the soldering iron, just regular solder, just put it on there. And then you add a little bit of flux on top to make sure it flows good in the oven. You set your part back on there, and then you put it in the oven, and it reflows really good. Okay, and then we're also going to do the little the oscillator for the microcontroller, because it's really hard to solder with the ground plane, and we're going to solder that in the oven. All right, so now we'll squirt a little bit of flux on it, make sure it all works good. That should do it. Yeah. Very gently put it in the oven like that. Auto execute should be F1, and we should be rolling. Yeah, there we go. It's starting to heat up. There it is, folks. See what it looks like. It looks like it baked the hell out of the flux anyway. Okay, this is what it looks like when it came out of the oven. You can see the flux. I had quite a bit on there. And it baked it. That round black spot is some contamination that was on the board. Got baked in. But you can see the solder around the pins are really good. I mean, it looks really good. I wish I could get better pictures out of my microscope. I'll have to work on that, but it looks really good. Okay, so the next thing is let's get some parts on the board. Okay, that wasn't so bad. It was like magic. Okay, so we are got all the parts on the board, so we're ready to like test it. First, let's go over what's on the board and the different sections, modules, whatever you want to call it, on the board, and then we'll start knocking them out one by one. Okay, so here's our I/O board, and I'll go from left to right across the board and describe what each component does. So first of all, right here, we have our main I/O connector. That's where the ribbon cable plugs in. That's the one we have to solder in the oven. And so then over here, we have, this is to set the board address. So you have 1 through 7 for the address. If you put it on 0, that disables the board, so it cannot receive any address. Therefore, it will never take control of the bus or put any data on the bus or read from the bus. It's just inert. It's out of commission. It can sit in the system, but as long as the jumper is right here on 0, that's kind of backwards. Let's do this. Then 0, then it's the main brain doesn't see it in the system whatsoever. All right, so then we have U4 and U6. No, U4 is the 138 address decoder. So when this address from main brain comes in and hits this decoder and it matches this, what you have, the address you have it set at, then it sends an interrupt over here in the microcontroller. All right, so this is the microcontroller right here. All right, so then this one and this one are the address buffers. So they're a one-way buffer. They're traveling out to the SRAM with the addresses. All right, so when you read and write, and then you set the address, read and write through the PMP in the microcontroller, then it sends the addresses out onto the bus once these are enabled. All right, so then this one right here is the data buffer, and it's bidirectional. So the data comes in and out through the connector from the SRAM, and it goes through this buffer and hits the microcontroller. And so the buffer disables any bus activity on the SRAM until you do a read or write. That way, there's no bus conflicts from other boards on the bus. All right, so this I/O connector here on the ribbon cable is shared by all boards in the system, including main brain. They're all shared and access the SRAM in different blocks. So that brings us to this jumper right here, and this is your A10, A11, and A12 jumpers. And so you can combine a binary value here to set the base address of uh, of this board, and it comes in 1024 or 1024 bytes or 1K of memory space in the SRAM. So that's how you set it here. And no two boards can have uh, the same board address or the same base address. They both have to be different. All of them have to be different. So each board in the system has to have separate addresses. All right. So then right here, we have a reset. And this, if you take this jumper off, it disconnects the reset from the ICSP here, which is the programming port for the microcontroller. So when you're programming the microcontroller, it usually doesn't matter, but the option is there to remove this, and that way you have a direct, uninterfered with connection to the microcontroller with your programmer. And then when this jumper is on, then on the back side of the board is a reset supervisor chip. All right. And that generates the power on reset for the microcontroller. So if this jumper is off, the microcontroller will not get power on reset. All right. So then this is our flash chip, and it's a 4 megabyte, which is 512K by 8 bits. So it's 512,000 bytes that you can store in here, which is not too bad. Nothing to brag about, but it's a considerable amount of storage for an embedded system of this size. And then this right here is the oscillator that generates the clock for the microcontroller. So then up here, we have our LED port, which is divided into kind of like two sections, but it's an 8-bit port, 2 nibbles, 8 bits. The green one being the most significant bit in the system. You could also move this down and have it the least significant bit if you wanted, however you want to do it when you assemble a board. So then we have some I/O connectors here. We'll flip the board over and take a look at those. And so then we have, okay, so this jumper here is the output of the DAC. So the DAC can put out a AC signal or a DC signal. So if it's an AC signal, it goes through a cap. So if you want to send, like when we do our composite video signal, then it goes through a cap. Some depends, though, you don't have to, but it goes through a cap to block any DC component. All right, so that's just a jumper here, AC or DC, and then it comes out on this one of these up here. We'll flip it over and we'll look at that. And so then we have a diode here for measuring an AC signal with the ADC. And this is a analog switch. So it acts like a selector on your digital voltmeter for different ranges. So there's 8 possible ranges. It's split into 2 sections. We'll get into that later with the data sheet. So over here we have 4 different values that we can, 4 different ranges that we can read. So I have it kind of set up for 3 volts, I think 12 volts, 24 volts and above. It doesn't go really above 30 because once you get into like 100 volts, then you're getting some blasting capabilities happening. We don't need to go that high on this one. I think 30 volts would be the highest you would need to go. And so then there's just a divide by 2 splitter here, a voltage divider that cuts the voltage in half. We can change that with these resistors. Um, so then this whole section right here is your digital switches, and these are the MOSFETs right here to do the actual switching of the load. And this is your diode from the circuit we went over in the previous video. These are the diodes to cause a voltage drop across the diode so that our load can work properly and not be on when the MOSFET is switched off. And that's pretty much it. We have a PWM output right here. And then we have two universal outputs, digital outputs, 3.3 volt outputs. And then we have an op amp in. It's just a regular op amp that's internal to the microcontroller, and it's the plus and minus input just like any op amp. So you could build you some kind of amplifier circuit or comparator or something of that sort. Okay, so let's flip the board over and we'll look at what these outputs are, these connectors. Okay, so here's the bottom of our board. Not much to see here. I should have cleaned it a little bit, but there's really not a lot going on down here. So right here is our reset supervisor that we were talking about. And then this is that jumper, the reset jumper. That's our ICSP programming port here. So this is the front of the board. This is right here is where the main ribbon cable connector is. I call that the front of the board. So then I have it set up here for some mini switches or mini sockets but you can put whatever connector you want on here. I haven't decided exactly what I'm going to do for connectors, and that's for future development. But so here's the comparator in, and that is for the DAC comparator. We'll get into that later. You can do some tricky stuff with that. And then DC in, that's where you measure the voltage, DC voltage going into the analog to digital converter. So that jumper that sits right here will switch between this one and this one, depending whether it's DC or AC. So you can actually have two signals running on here at the same time, but only one gets connected with the jumper. All right, and then this is your DAC output right here for the digital to analog converter output. And that's what we use for when we do our composite video thing. All right, so that's pretty much it for the back side. There's some, we got some resistors right here for the pull-ups for our base address. And that's everything over here. That's about it for the back. Not much going on the back. All right, now we can move on and do some deeper diving into it. So one of the things that became a little interesting, so to speak, was adding the flash, because with the flash, it's 4 megabit, so I think that's 512K memory locations. And so to address it, you need to go A0 through A18 on the addresses. And we don't have that many available because we got our just basic addresses for the SRAM. and our base address and 1K space in SRAM. So a lot of the other ones got used up, and I don't think the microcontroller can go all the way to A18 anyway. I think it only has 16 address lines. But anyway, so we have to use IO lines that are available. And those are just kind of sparsely populated out into the different ports. So there's 3 ports with the address lines on it, and we have to what they call bit bang it. So we're just turning them on and off when we need to on that address. There's no automatic address when we set the address like we do for the SRAM. So that's interesting. So I had to write some code, and it took some time, and I had some problems. And so that's a good troubleshooting thing, is to show you what the actual problem was. So uh, let's just take a quick look at how we're addressing and interfacing the flash memory to the microcontroller, and describe the problem I had and what the solution was and how I found it. All right, so let's start with that. Okay, so let's open up. Let's see, where do we want to start? Let's look at the schematic first. All right, so this is the schematic of our I/O board. This is the microcontroller, and this is the flash. Uh, I'm not responsible for the chip sizes on the schematic. That's the way they come when I download them. Sometimes I modify them a little bit because they have stuff I don't want, or they have the different pins from a different manufacturer or something. But anyway, this is our flash memory. So if we take and put it on our eyeball, and we look at the memory location or the address lines, so from A0 up to A through A9, that all goes from the PMP, PMA9 right here. So it could be PMD9 if we were using 16-bit. So then you run into, you have to multiplex. But anyway, we're using 8-bit. So this is PMA9. And that's just when you write to it, you set the address for the PMP, and it just automatically sets the address from of the 0 to 9 lines. All right. But then when you come up to A10 here, then we're out of address lines because where our IO takes so much, and you can't move the IO around and not so that you can use the address lines at the same time. Like the DAC and the ADC and some of the AN, the inputs and stuff, it interferes. So from A10 up to through 1018, A18 is we're on our own. So this one just happens to be RD9. All right. So then once you get up here to A18, A17, there's A18. All right. Once you get up here, and see, that's RE10. So we're using the 3 different ports to generate the addresses for the flash. And that slows us down a tiny bit, but it's okay. It works for us. So then that's what we want to do, is to come over here to our code, and we'll scroll down. This is our main code for the IO board. It's called IO board C. So here's the first. Let's see, do we have anything? LED port. Okay, so we do the PMP. We initialize the PMP. So then we initialize the flash. So the chip enable is RE8. Then we have A10 is RD9, A11 is RD8, A12 is RD7, RD6. Then it goes to RB5, A15 is RD5, RB6, RE11. See how it jumps around? So we have to write code to make an address from that. So I wrote some code here. It's called a function called set flash address, and it passes the address that you want to set. So you would call set flash address, and if you wanted to write to address 1FF, then you'd put that in there. So then you have to do a little switcheroo here with the variables, because other functions might use, and probably do use, FM address, or they need an address. So this is more or less like a local variable. This is a global variable. So once it's loaded to FM address, other things can read FM address, and it did work. That was one of the problems, was I had to do this to make it work. And ChatGPT actually helped me figure that one out. All right. And then another thing is, once you set the address, then once you hit, see, this is a 16-bit microcontroller. So once you hit A15, which is the 16th address bit, then you're moving this around registers and stuff, it's natural when you define an integer, the native integer in a 16-bit system is 16 bits. So you got to keep your eye on that, because then it doesn't read anything above that 16-bit in your variable. So you have to make it a unsigned long. And then when you do that, then it will make it into a 32-bit variable, reserve 32 bits for the address in memory, and then you can go all the way up to A18. So that was another problem that I had to work out. So then we have to load the lower bits, 0 through 9. So we'll just take this FM address, make it a 16-bit, cast it to a 16-bit, put it in our PMW address, all right, our PM write address. And then there's also a PM read address. That will get you. It got me. That was my big problem that I had a hard time figuring out. We'll get to that in a minute. So then you don't necessarily have to, but I wrote this function to just reset the flash address when you're done. You just put it at 0. You don't, I might just take that out. It might just be unnecessary. But when you're writing code, a lot of things you try different things, and some things you cut out later. Okay, so this is the write. It's just a standard function. You pass the address and the data, and you do have to do the same thing. You put it in new variables, and it goes down. It does some regular PMP stuff that we went over before. I did a small delay, and it seemed to help things stabilize a little bit. I'll have to do some tests, see if we want to take that out or leave it in. I think this is from the data sheet. So once you read, let's see, PMD out, yeah. So once you write the data and the data completes, you have to wait 20 microseconds for the internal processing of the flash. All right. Then you deselect it. Same thing with read. You just pass it the address. Here's our FM address again. Going through. Same thing. Regular PMP stuff. There's that reset flash address that we might cut out. And then this one returns the FM data. So you can use a return to pass the data that it reads. All right, but you don't have to. Sometimes they use it, sometimes they don't. So now we have a flash chip erase function, and that just erases the flash chip back to FF 0FF hex. And then I've reset the flash address. You have to do a little bit. You have to wait for it to complete. And we'll do some testing on that. We want to lower it, make it a little bit leaner to waste less time. Time is of the essence. So then this is one of the things you can do is to get the flash ID if you want. And so if it's a 1 megabit or a 2 megabit or a 4 megabit, they have different variables that tell it when you read it. And all the flash that has these special sequences that you have to do before you can access it. The read is the only one that you don't have to. Anything else, writing, erasing, getting the chip ID, always has to go through a 3-step sequence so that a random noise or some kind of bus glitch can't access the flash accidentally. And you can refer to the data sheet on that. So I think, do I have the data sheet? Yes, I do have the data sheet. Our data sheet is right here. It's the MX29LV040. And since they discontinued the package, and I have to use that same package because I already had the boards made, then I'm using the 010 because I had those in stock. But that's just for this chip, this board. All right. And so what else we got? That's about it. That's all we got for the flash. So that's how we do the flash. So now back to my big problem. And the problem was that I overlooked the fact that there's a PM write and a PM read. So when you're writing to the flash, the PMP requires you, since we're using double buffer mode, it requires you to do a write address, and when you read it, you have to do a read address. And so I had overlooked the read address part, and I just could not get it to work. So the way I did it, I just went step by step until checked every address line. I checked every data line. I looked at them on the scope to make sure they were clean, that there was no glitches, that nothing was being pulled down or anything like that. And I went through all 0 through 18, all 19 address lines. I went through all 8 data lines, and I checked the read strobe and the write strobe and the chip enable, and I compared like 3 or 4 of them together. And finally, I was getting really close to getting beat up and just giving up. But I noticed this, and I'm like, and it started working. Because it works great on the same chip, works great on MainBrain's board. So there's no reason it shouldn't have worked, and I was just banging my head. And finally, I figured out what I did wrong. Just by going step by step, very methodical, not giving up, just eliminating possibilities. And finally, I found it. And that's the way troubleshooting works. That's very important. Okay. So that's the flash, how we're doing the addresses. Okay. So that's how the flash works. So now I wrote a couple little applications for the Windows program so that we can read and write to the flash, just 1 byte, just to test it. And it also proves that we can transfer data back and forth with our front end. So that makes sure that's working. And it does seem to work pretty good. So I think we're looking good on that. So let's pop up the app and I'll show you what I got. Okay, so let's open up our MainBrain Windows Utilities app here. All right, press any key to connect. I have a new menu item, applications. We're going to get into that later. But right now we'll go to Utilities, Peripheral Commands. All right, so we have 3 new ones. We have Read Flash, Write Flash, and Flash Chip Erase. So first we're going to read the flash. So click on that. We have to set our board address as 2. That's what it's set at right now. It has to match our board that we want to talk to. And we'll just go with flash address 0. Doesn't really matter in this case. So we'll double click on it. And you have to do it twice because I don't know for sure, but I mean the data transfers from the I/O board, writes the data, it reads the flash, writes the data into the SRAM, and then mainbrain reads the SRAM, sends the data to the USB. The USB sends it to this application. So all this moving around, it's like a double buffer type thing, I think, and it just has to do it. It's not like a glitch or like only does sometimes, but it's very consistent every time. That's the way it has to be. So that's, I got to look into that and see why or what I can do about it. And so that's another issue we have to study. And but that is accurate data, and the flash is erased, so that reads FF hex. So anything in here is hexadecimal. All right, so then we want to write a value. So same address, we will put say 67. We'll write 67 to it and double click it. All right, so sending it over, you don't have to double click it twice for whatever reason. So there's something about transferring it back that has to do it. All right, so if you look at what mainbrain's doing, it changes into a peripheral menu. I have a little bit of thing going on there. I haven't addressed yet. And then we have down here, we have our commands showing up onto the I/O board LED port so that we know which one we're writing to, just for a little bit of troubleshooting and status. So then we supposedly wrote 67 to the address 0. So then if we come up here and we read the flash, so if you double click on it, it clears it out for you. All right, so then we double click it again and it reads it back 67. So then if you check a different address, like 2, and you read it, then it goes back to FF. All right, so that means everything seems to be okay, right? So then if we come back to 0 and we double click, 67. All right, so then if we take and we go down here and just double click on chip erase, all right, then we come back up here and we read it, then it's back, it's cleared again. So it's erased. So everything on the flash is working good, pretty smooth. There wasn't any glitches. I haven't found any problems yet. I'm really happy with it. So that we can move on to the next fun. and fun it will be. Okay, so that's kind of it for today and for this video. And so we know that our flash, we can read and write and erase the flash. And so that means we can store stuff in the flash, like a waveform or just data for an array or something, a table, all kinds of stuff. There's a lot of applications. And 4 megabits, it isn't a lot, but it isn't a tiny amount either. You can work with it real well. And so then probably the next thing to do is explore those applications I was talking about. So we'll do that in the next video, and I will see you there.